Hi there, my name is Daniel, and today I'm going to go over my off-grid solar power system that I designed to charge my Tesla. So, kind of the drive behind this was that I really wanted to drive my vehicle from the sun, powered from the sun. I didn't necessarily want to power my home with PV because we may be moving at some point to a bigger home, and I wanted to design something that I could take with me if and when we leave. So originally I had thought maybe there could be a hitch system or a trailer system where I could unfold panels and go that route. But turns out I don't have enough space for a trailer, and the worry of it being stolen, and so essentially I decided to make a system with panels on my roof and go that route. So the system itself consists of 16 panels, 4 of which are Hanwha, the kind that Tesla sells, and 12 of which are Silfab solar panels that are made in Washington. The electronics and batteries are made by Victron Energy out of the Netherlands, and Battleborn batteries, lithium-ion batteries, made in Nevada. And so those batteries and the Victron components work well together. And there's a lot of examples on how to set everything up. And overall, I have around a 2.7 kilowatt maximum power output from my solar array that charges my batteries during the day when I leave. And then when I come home, I can discharge the batteries into my car. And that, right now, I have around 10 kilowatt hours of batteries, and so that's good for about half a day's worth of PV. So if I charge a bit in the morning using the sun, leave during the day, charge in the evening, and then discharge whatever's been charged into the batteries while I'm gone, then that's more than enough in terms of mileage that I drive on a daily basis in my Tesla. So that being said, let's go ahead and go into the garage and check out the system. Okay, so we'll begin looking at the front panel of the system. We've got a monitor up top that tracks the inputs and outputs, an on-off switch, a battery monitor made by Victron, a solar charge controller made by Victron as well, and then two 3000 volt amps, or basically 2400 watt inverters. These two inverters are connected in parallel by the blue cable down there, such that, in series really, such that they can produce 240 volts output to this output box right here, and then also 120 volts if I need it for cooling fans, etc. So the total system capacity, continuous, is 4800 watts, 4.8 kilowatts, and that's if the temperature is fairly cool in the garage, and it's derated a little bit as the temperature rises. The PV input currently exists of 16 panels, which is a little bit overkill for the charge controller. This charge controller can output a total of 100 amps, so the 100 down here. And based on whether you have a 12, 24, or 48 volt system, you're going to either get 1200 watts, 2400 watts, or 4800 watts. I have a 24 volt system, and right now I'm outputting 2700 watts, and that's because the battery voltage is at 27 volts, not 24 volts. So right now this is basically the peak power output for this single charge controller. If I wanted to increase my peak, then I could get another charge controller, but right now this is sufficient. So if we move in and look at some of the input parameters, or output parameters I guess, for the unit. Right now I'm charging the car very, very low so that the no fans and the inverters are on, so it's nice and quiet, at 1.2 kilowatts. Okay. My battery bank is sitting at 36%, and I am currently charging the battery bank at 1300 watts. And my total PV charge is my total PV input is 2600 watts. And if you add up these two numbers and subtract the, if you add up these two numbers and subtract it from the PV charger input, then you'll calculate the loss. And right now at this really low charge rate, the loss is about 10% in the inverters, and that can drop as low as around 18% or so once you're really cranking. So you can see at this voltage, my battery voltage is around 27 volts. I'm charging the batteries at 50 amps. Okay. And then we can also look at the monitor on the charge controller and look at some of the inputs. So again, 2700 watts right now. It's the battery voltage, output current into the batteries and also to the car or to the inverters is 100 amps. So my PV voltage is 131 volts. So that's what it's currently set at, or that's what it's currently determined to achieve 21 amp output. Now, again, there's too much PV for this inverter right now. It's sized for the winter, so as the sun starts falling throughout the seasons, I'm going to get less and less PV. So it can handle too much PV. This is the temperature of this unit. I have a fan mounted behind here that I currently have turned off. And then the battery temperature right here is 21°C. And we're back to the 2700 volt output. Alright, so I'm going to go in the car, and just to prove everything is actually charging, you've got Tesla charger, happily charging away, cable running down into my Model Y, and if we go into the vehicle, we can see that we are charging away at 239 volts and only 5 amps. So I can go ahead and crank this up to around 15 amps. I like to keep it no higher than around 3.5 kilowatts. Okay. And we can step back and check out our monitor, and now we see that my AC load is 3.5 kilowatts. Each inverter is outputting that much power. And now I am drawing 1300 watts from my battery. Okay, so if I want to leave for the day, which I'm going to do soon, I want to drop this down to around 20%. That maximizes my lithium-ion battery lifetime. So I'll drop that down, unplug, and then the PV will charge my batteries throughout the day. Okay, so what exactly is going on here? My PV input comes out from the roof to this outlet box where I'm pointing to, and then it goes into the back. We'll go through the back. So that's DC power. Again, it's 4 residential panels connected in series, and then there's 4 of those 4 panels connected in parallel. So each of those panels, each of those clusters of 4, has an open circuit voltage of 160 volts or so at around 25 C. And the standard test conditions say they should have an output current of around 10 to 9 amps. Alright, so temperature and seasonal fluctuations change both the voltage and the current. And the panels clearly don't operate at the open circuit voltage. They operate somewhere lower than that, near the max power point. Alright, and right now you saw earlier that the charge controller is choosing to operate at 131 volts. You can hear the fans for the inverters just kicked on, and that's because I'm charging at a fairly high rate. So let's go ahead and look at the back of the system to see what exactly is going on. Okay, so again, PV comes in from the wall. Right, there's external circuit breakers that are outside to protect this DC current coming in. So right now, the wires are cool to the touch. Okay, there's about 131 volts and 20 amps going through here. That goes in through the back to the charge controller. Okay. And then the charge controller converts high voltage DC to low voltage DC, and also finds the maximum power point of the solar array. These 2 big fat cables, these are 2-aught cables, carry the current that is supplied by the charge controller. The positive goes through a 200 amp fuse to a main disconnect. Okay. And all of this is low voltage, and so it's safe to touch, but I generally don't touch it. Okay. And so this is the power coming in from PV, and this is simply a switch. Alright. When the switch is on, it's going to take the power from the input and connect it to the battery bank. Okay, so this lead goes to the battery bank, okay, and there's a large bus right here for the positive terminals. Okay, so we've got power coming in, okay, and then all of these are connections for the 8 Battleborn batteries that I have. So each of these batteries is around 12 volts nominal. It's more like 14. They're all connected in are connected in parallel. Series. And then there's 4 parallel banks of 24 volts. And so this mess of wires has to be this way because all the leads have to be the same length, so that the resistance is the same, so that all the batteries charge and discharge at the same rate. Okay, so looking at one pair of batteries, you can see the negative is here, positive of one is here, connects to the negative of the other, and then the positive here comes to an additional fuse, okay, and then that goes into the main bus. And then there's 4 fuses for all 4 battery banks. Okay, so that's the power. So each one of these batteries is rated at 1200 amp hours. Alright, so multiply that by 8 and there's roughly 10 kilowatt hours here of power. Not quite. So that's 10 kilowatt hours of maximum storage, and since they're lithium iron phosphate, you can cycle them from 100% to 0% to a basically without harm, and there's an expected life cycle of around 5,000 cycles. So that's many, many years of cycling. If you go down to 20%, it supposedly can double that. Alright, so if we come back in to our main switch, okay, the disconnect disconnects the batteries, okay, and then from either the battery or the PV, there's two large 2-aught gauge cables that go into a single fuse behind here. Okay, that's a 250 amp fuse, and then out from those go power lines into the inverters. Okay, so that's DC power going into the inverters, and then coming out of the inverters is this very large AC wire. Okay. And so there's two inputs coming into a circuit breaker box. Okay. So the 240 volt is a double pole 20 amp circuit breaker, and 120 volts can be pulled off of one of the legs. I'll explain that a little bit more in the future here. Let's see if I can get that closed. I'll leave that. So what else is on the back here? Down on the bottom is a temperature measurement in black for the battery, and then also a battery monitor cable. One of them is connected to the main battery voltage. Let's see if we can get that in focus. So this is the main battery voltage, and then an additional one is connected to what's called the midpoint voltage, right in there. And so with series connected batteries, there's no guarantee that both batteries are going to be at the same voltage. So you want to monitor that and make sure that the batteries are charging and discharging at equal rates. And if they aren't, then you should take it apart and charge the batteries up 100% to basically neutralize the voltage across them. So we can talk a little bit more about the batteries. They basically have a battery management system, or BMS, built in. When they charge up, they increase in voltage to a set point, which is called the bulk charging phase. Okay, and once a certain voltage is achieved, the batteries are held at an absorption phase of, in this case, it's 28.8 volts. And inside, once higher than 14 volts is achieved across the battery, the 4 individual cells inside here equalize their voltage. Okay, so it's said to try to bring up your system to 100% charge at least once a week, so that all the individual cells in all of the batteries can normalize their voltage. Now, there is no way to automatically make sure that, say, this battery and this battery are the same voltage, as I was discussing earlier, hence the need for monitoring the midpoint voltage. And so what exactly is going on in terms of the monitoring? Well, it's achieved by a shunt. Okay, so there's a single terminal on one side that goes to your battery bank, and then everything else is connected to the other side of this shunt. So this is a very low resistance path, and basically it can monitor how much current is flowing throughout the system at any given time. So it's monitoring not just the voltage across the batteries, but how much current, because it's not sufficient to just look at the battery voltage to determine whether or not your battery is fully charged or not. You have to look at the actual amount of energy. So knowing the voltage and the current, they can calculate how many amp hours are going in and going out of your battery at any given moment. And then you can see that basically an inverter is tied to ground here, the charge controller is tied to ground here, the other inverter is tied to ground here, and then this particular cable is just a large cluster of equipment grounds, okay, and then this particular cable is the system ground. So this system ground okay, is connected with an MC4 connector to a copper rod in the ground, and that's separate from anything in the house. Alright, so I drove a copper rod into the ground, and this is system ground, and then these two are my PV inputs. So you might ask, well, why did I design it this way? Well, I wanted it to basically be easily unpluggable from the wall, such that it can be moved anywhere I want to put it. So if I move houses, if I want to take it with me on a trailer or in a truck, this whole system can be rolled away and moved very efficiently. So if we go back to the front, just sort of go back over what exactly is going on here. Again, PV input comes into here, down here, and that's low voltage or high voltage, low current, and then low voltage, high current comes out. This is again the low voltage, high current DC power, goes into the inverter. Okay. And then one leg of the split phase comes out, and then on the second inverter, same thing. So if you're not familiar with split phase power, essentially you have two 120 volt lines that share a neutral, and they're 180 degrees out of phase, such that the peak of one of the sinusoidal curves overlaps with the minimum of another leg of your curve of your power, of your voltage and current, and the difference between the two is then your 240 volt RMS voltage. And so, since we're sort of wrapping up this portion of the program or of the video, charge controller is sitting at 54C, which is, warm to the touch. And so I'm going to go ahead and plug in the fan. And I generally keep this fan plugged in. It's an AC fan. It consumes 20 watts. And within a minute or so, this temperature of this will start dropping. So right around to room temperature. So it's advertised that the charge controller is extremely efficient because it doesn't need a fan, but I've seen this thing getting up to 65C, and that's just any kind of high temperature is not good for electronics, so I go ahead and cool it with a fan. So in terms of the overall construction, this is HDPE plastic, 3/4 inch. I found it to be really, really tough and also machinable. So, you can cut things out of it and you can screw things into it really well. The chassis is essentially just electric conduit mounting brackets, available at any electrical or electric supply store or Home Depot. At some point the whole thing will be enclosed but for right now it serves its purpose. And it's on wheels, so it can move freely if I need it to do so. And so go ahead and move it back into its normal position, and that's it. Okay, so one of the nice things about Victron components is both their interface, hardware, and then the interface on the web. So this screen is connected to the brain in the back. I didn't really go over that. It shows basically your inputs. There's also a section for a charger. You can plug this into the wall and charge your batteries if you want. And if we go into the menu, you can see the 3 items that I have, which is the battery smart monitor over here. I have 2 Multiplus 300 amp hour inverters, and then the solar charge controller. So this particular unit is Wi-Fi connected. Okay, so it takes all the data and can dump it to the internet. And if it loses internet connection, it's got a memory card in here, and it can store weeks of data on that memory card. So occasionally there will be alarms. You can see some notifications, some low battery notifications. The inverter settings, or excuse me, the solar charge controller settings. Okay, it's got a number of them. Multiplus settings. These are both set here and on an app on your phone. That's Bluetooth. Most of the settings are set on Bluetooth. And then the smart battery monitor. So here's where you can see my top voltage. So that's one of the battery's voltages, and this is the second battery voltage. And the midpoint deviation is 0.1%. So again, that's only for one of the batteries. So it's good to go through and periodically check, in my case, the other 3 banks to make sure that everything is charging really well. And in general, when the batteries are in use, you see no deviation. It's when they're fully charged is when you start seeing any kind of deviation, because one of the batteries may be a little bit low compared to the other. Okay, so here I have the Victron, it's called VRM online software. It's really great. So you can move these modules around if you want to, but currently what I have is my battery state of charge right here. You can see it was steady throughout the night. It dipped when I started charging slowly, and then I've been charging quickly here. Over here is the battery voltage across both of the batteries of the 2 that I'm monitoring. Over here is I have my PV power as a function of time throughout the day. You can see that I've got quite a bit of shading going on due to trees in the neighborhood, and essentially, you know, at some point in time during the day, I hit around my peak 2700 watts, and it sort of looks like a tabletop. I've got a battery summary here. In the middle, I've got information on the solar charge controller, including the yield so far today of 8.16 kilowatt hours. Yield yesterday was 16 kilowatt hours. I have output, AC output parameters over here, and then you can see down here is my AC output on both phases, and also the total output So in the morning I was charging slowly, and then I cranked up the power more recently. And then down here you can see both the solar charge current and voltage, and up here the output voltage and current of the solar array. So the output voltage of the solar array in the morning is 100-ish volts, and then the current slowly rises up in orange, and then right now we're lingering around 140 volts or so, and 20 amps or so output. And again, that's going to change with different shading conditions and whatnot. So there are no micro inverters on the solar panels. They're simply connected the old way, where everything is either in series or parallel. But panels are so cheap, you can simply overpower as long as you have the roof space and get what you need. Okay, so here's just an example of the 4 hand watt panels that are not mounted on the roof. So 12 of them are up on the roof permanently, and this is sort of my experimental boost zone, if you want to call it that. It's on ground mounted unirack. It's on a ground mounted unirack system, and of course it's on wheels because I like it to move around, and basically I can try to avoid shadows throughout the day if I'm home. Nothing fancy going on here, just again it's 4 panels all connected in series. I've got a little current meter over there that I can kind of check up on it throughout the day if I'm bored. Overall, this has really helped create that flat top in PV that I was talking about earlier. And again, I have this primarily just for fun and as a boost zone. I purposely have it set at a very high inclination angle, 45 degrees, because as these trees lose their leaves in the winter and the sun starts falling south, this panel will get more and more power. So this is a rated 1280 watts, but I draw a lot less than that due to the charge controller, which is currently maximized at 2700 watts. So okay, so that about wraps it up. Hopefully everything is fairly clear. I didn't mention I have iron ridge mounts on the roof, ballasted, so that all I have to do is unscrew the panels and remove the bricks, and then get them off the roof with a friend and take them anywhere I want. And this guy will have to be disassembled too because it's incredibly heavy. So far it hasn't taken off with any kind of strong winds. I don't think it will move even with wind due to the turbulence here in the backyard. But there we go. Tesla can be charged by off-grid solar.